Warning: this video contains in-depth and graphic footage, images and exploration of various highly invasive surgical procedures. Viewer discretion is advised. The Spartan-IV Augmentations are the most survivable but also the most comprehensive list of augmentations yet given to humans to make them into super soldiers. Project Orchid, its given codename, was an advancement of the augmentation sets given to the Spartan-IIs and Spartan-IIIs respectively, with end goals and implementations achieved by hybridizing the way in which the Spartan-II and Spartan-III augmentations were performed, while also addressing the fact that these were fully grown adults that were being augmented versus the morally and ethically debatable prepubescent teens, and as such were working with bodies that had already fully matured and achieved their natural homeostasis, so to speak. I've done most detailed breakdowns on the Spartan-II, Spartan-III and Spartan-IV augmentations, Project Aster, Chrysanthemum and Orchid respectively, and I've also done a look as to whether or not the Spartan-II and Spartan-III augmentations are actually possible. Well, up until now, I've left the Spartan-IVs out of that equation, and now I'm going to fix that. So let's look at Project Orchid, the Spartan-IV augmentations, and see as to whether or not they are actually possible with modern day science and technology. Hey everyone, welcome back to Installation 00, and to kick this off, let's just do a quick skim over the augmentations for the Spartan-IVs. We have the Torpid data cluster, which is the new form Spartan neural interface. This is an upgraded neural lace or superconducting filament that's threaded through the midbrain of the host and extends to a data port at the base of the skull. It facilitates Mjolnir's functions of being able to translate thought to motion seamlessly, alongside supporting an artificial intelligence. They received the Muscular and Skeletal Engineering series, which is a series of augmentations designed specifically to re-engineer their muscles and bones to make them stronger, tougher, faster, and less prone to break. The Neurological series is where their nervous system is supermyelinated, increasing the speed of neural impulses and thus the subject's reaction time. The Spartans are given organ implantations where practically every organ in their body is altered or replaced to some degree. They are given immense circulatory and metabolic improvements, given a series of gene therapies implanted with some biomonitors, and given final end cap augmentations which regulate their hormones as well as archiving their bioprofile. Again, full details can be found in the most detailed breakdown of Project Orchid. But just how possible is it to actually make these augmentations in real life? Well, let's start from the top. The Torpid data cluster is basically a brain-computer interface. We are developing these right now. In fact, Elon Musk and Neuralink are developing a brain-computer interface at the moment that can be implanted into the host's brain, can be flush with the surface of the skull, and can pick up an impressive amount of neural activity within the skull. Now, when considering that the neural interface's primary function is the connection between the Spartan and their suit of Mjolnir for the sake of movement, you have to then consider that there are two major centres of the brain that we should be taking signal from. That's the cerebellum and the motor cortex. We already have electrodes capable of detecting brain impulses from both within the cranium as direct implants into the brain matter, as well as from outside of the cranium and everything in between. By this I mean that we can have, for example, a skull cap with an array of EEG or electroencephalogram sensors that can pick up impulses from within the brain but is non-invasive. Admittedly, the resolution of these impulses isn't tremendously high, and as such may not, at least until further advancement, be useful for translating thought to motion. Electrocorticography is when an array of sensors is implanted within the skull intracranially, but against the surface of the brain, but not actually invasive into the brain matter itself. This boosts signal resolution for detection, but again is highly invasive and at least at the moment requires relatively major surgery. So really in that regard, our best bet is something like Neuralink, small electrodes that can be implanted into the brain material by a robot that can plant them extremely precisely. and you'd need a series of advanced filaments touching both the motor cortex, the midbrain, and the cerebellum to get the best of the thought-to-motion effect that you're trying to achieve. So this is achievable, but right now it's still a way off. And it's also worth noting that the visible port that is on the base of the skull on most Spartans, that's actually possible. You see, the port would effectively be a titanium interface. Beneath that port would be microelectronics that connect directly to the neural lace, but the actual surface of that metal would effectively be occupying an open wound, for lack of a better word. This would be subject to infection unless, of course, the plate itself has a surface that is macroporous, so that once it is put into place, the skin, the open wound, so to speak, can grow into the titanium plate to a degree and seal the wound. This is actually an active part of research at the moment in regards to osseointegration for use with amputees and prosthetic limbs, whereby a prosthetic limb can be connected more structurally to the body via a direct metal shaft implanted into the bone of the residual limb, and the prosthetic limb effectively locks onto this implant as it protrudes from the skin. Again, where it protrudes from the skin is effectively an open wound, and although there are some barriers that can be used to prevent infection, it still happens from time to time. Looking at engineering the surface of the metal there and allowing the skin to grow into it somewhat would seal the wound, so this is still ongoing research. Next, the muscular and skeletal engineering. Now, first and foremost, let's talk about the bones. The bones are lengthened and then reinforced with a fullerene lattice, which is regarded as being tougher than steel and making the bones practically unbreakable. Again, bone lengthening is something that we can do now. There is such thing as a height augmentation, where effectively they break the bones of the femur and the lower leg and create a small gap between that break, allowing the break to slightly heal across that gap and then break it again and pull it slightly further apart, adding bone material and length to the bones overall. This augmentation procedure at the moment is limited up to about 4 inches of additional height, but with advancement in technology and surgical implementation, it's entirely possible that bone lengthening can be increased tremendously. And with continued advancement in certain engineering practices, in particular relating to titanium and 3D printed micro and macroporous surfaces, it's entirely possible that a femur, for example, could be broken, moved apart by, say, 4 inches, and then a titanium insert is placed into this newly created gap that matches the profile of the bone itself, but whose ends are engineered to be micro and macroporous, so that when the bones are bolted to this newly created insert, and the bone osteogenesis process takes place, new bone material can actually grow into the surface of the titanium implant, increasing the strength of the connection between metal and bone. The skeletal reinforcement can be achieved via this fullerene lattice. Now, this is basically a carbon nanotube, or more accurately a lattice of atoms bonded together into a continual hexagonal pattern. Fullerene in the modern sense is carbon nanotubes because it's one of the few materials we can actually do this with at the moment. It would be effectively like wrapping the bones in graphene. And whilst graphene is pound for pound stronger than steel, when we're talking about single layers of carbon in a carbon nanotube wrapped around a bone, there's going to be negligible increase in the bone's strength, shear or fracture toughness. That is, of course, unless this augmentation actually suggests that they're not microscopic atomic structures of fullerene lattices, but in fact macroscopic structures of metals woven into a hexagonal structure. In which case you could consider a titanium or titanium carbide or titanium diboride hexagonal chicken wire, so to speak, just a very, very fine mesh. Because it's titanium, titanium is biologically inert, which means the body doesn't react to it. If it's titanium carbide, it's an extremely tough ceramic. If it's titanium diboride, it's one of the toughest semiconductor ceramics in existence, and the boron would actually facilitate further bone growth. But the material properties as a consequence of an augmentation like this would effectively just mean that you would have a better elastic modulus. And for bones, that's not very useful. It's very rare that a bone is stretched to breaking point. In truth, it's a given that bones will likely only ever undergo compressive or shear forces, because any stretching forces, well, the person's joints and ligaments and tendons would give way first. So a macroscopic fullerene lattice of, say, titanium diboride wouldn't really help in compressive forces. It would give some assistance to shear forces and work best with stretching forces that the bone seldom ever comes into contact with. So while this one is hypothetically possible to wrap the bones and reinforce them, there wouldn't really be any particular gain involved in doing so. So the Spartan-IV's way of increasing the toughness of the bones, kinda pointless. Onwards from this, the muscles are augmented and injected with a protein that allows them to work much harder, and there's also increased growth and muscle grafting. If we're keeping on the injection side of the spectrum, then yes, we can probably do something similar to this at the moment. If you inject the chemical follistatin into the muscles, for example, follistatin is a chemical that inhibits myostatin, which is a muscle inhibitor effectively. We all have this naturally inside of our bodies. It inhibits on just how large our muscles can get, and there are some people that have a myostatin deficiency, which end up having much larger muscle mass and density. Giving yourself follistatin could give a similar effect. Injecting them with a material that allows them to work harder could be achieved, theoretically speaking, from a biocompatible electroactive polymer. This would be microscopic filaments of electroactive polymers that can react to bioelectricity or chemical electricity that is present within our muscles. Electroactive polymers work like artificial muscles. When subjected to an electrical charge, they contract with proportionally very high forces. Implanting tiny filaments of electroactive polymers that are responsive to bioelectricity could result in a massive increase in strength and power output. There are electroactive polymers that are responsive to chemical electricity at the moment, and they are, generally speaking, widely accepted as being biologically inert, which means that they can effectively exist within the body without causing inflammation or rejection in any way, shape or form. But again, to prove as to whether or not this is experimentally sound or practically possible would require human testing, and at least at the moment, unless a treatment or therapeutic option is brought forward to treat an underlying condition, it's unlikely that that's going to happen anytime soon. Next, the neurological series, which supermyelinates the nervous system. We can do this. We genuinely can do this. In fact, we've been doing it for a while. You can use stem cells harvested from the person's bone marrow and inject them in patients suffering from multiple sclerosis at sites where their own immune system has degraded the myelin sheath, and it results in the restoration of the myelin sheath, restoring movement and function to the person who may have lost function in that limb for a prolonged amount of time. So supermyelinating the nerves, basically giving this similar injection to somebody who isn't suffering from an underlying condition like multiple sclerosis, would result in an increased thickness of the myelin sheaths, and thus an increase in the nervous transductance. And now onto the organs. Virtually all other organs in the body are either modified or replaced in some manner in the Spartan-IVs. Generally speaking, they'll be replaced with alternatives that are more efficient at performing the job that that organ was responsible for than the biological organ is capable of. This is the case with the lungs of the Spartan-IVs, which are transplanted with biofabricated lungs that are lined with a Stonewall pulmonary surfactant, which is apparently a polymer that enhances the oxygen intake and allows a subject to process airborne toxins and foreign gas mixtures for a while. Now, while we don't have a finished article, we do have active research into creating artificial lungs, and our natural lungs aren't immensely efficient at actually harvesting oxygen from the air that we breathe. In fact, generally speaking, breathable air is only 20% oxygen, and of that, the exhaled breath contains 15% oxygen, which means, generally speaking, our lungs are only actually harvesting about a quarter of the oxygen contained in an inhaled breath for use in the body. And generally speaking, the need to breathe is actually pushed more so by the need to dump carbon dioxide buildup within the blood than it is to take in new oxygen. Engineering some artificial lungs that have within them a form of rebreather system that allows a single breath to be cycled back and forth between the lungs would allow more of the oxygen to actually be harvested from the single breath that is taken in. And as the carbon dioxide levels increase, it's nothing to say that a compartment of activated carbon that can absorb carbon dioxide from that recycled air couldn't be implemented, thus meaning that single breaths could last much, much longer. From a practical standpoint, at the moment, we don't currently have that level of technology, but we do have other organs that are artificial. There are artificial hearts, for example. There's genuinely people walking around at the moment with no heartbeat. Instead, they actually have a perfect sinus wave pump in their chest that pumps the blood through their body. By definition, they are clinically dead, as the metric that we use to measure whether a person is living or dead is whether or not they have a sinus heartbeat. There's continuing and advanced research in regards to the pancreas and replacing the pancreas with an artificial version. Even some emergent research in artificial kidneys, bladders, and livers are under active research. At this time, there are very few actual functional and clinically available artificial organs, but it's rapidly changing. On top of this, the Spartan-IV's eyes are augmented. Their corneas receive an implant that improves their eyesight and night vision. Again, I believe I've spoken before about the bionic lens by the company Ocumetrics, which replaces the biological lens inside the eye and focuses light 3 times more efficiently than the biological lens, allowing something approaching 60/20 vision. And on top of this, a TED talk by Justin Tipping Hall in regards to advanced material sciences, allowing photon captures and images, allowing visualization of infrared radiation, could be combined with something like the bionic lens to enable not only increased visual acuity but also night vision. So the eye augmentation is actually much more achievable in the short term than a lot of the other organ implantation therapies that the Spartan-IVs undergo. The circulatory and metabolic improvement sees the heart being given a polythread weave, which significantly increases the capacity to pump blood. Now again, going back to what we discussed earlier in regards to the muscles and being able to implant a biologically responsive electroactive polymer, this is basically along the same lines. Putting a electroactive polymer that responds to the electrical impulses that are given off by the muscles as they contract, and thus giving an additional contraction due to the deformation of the electroactive polymers, would result in a much harder, stronger heartbeat, being able to pump more blood more efficiently with less energy. Again, this is possible, but it's a good way off. Onwards from this, their blood composition is modified to allow for faster clotting and immunity against most toxins, as well as its ability to carry oxygen and wound healing. Engineering blood composition isn't really something we've touched upon yet in regards to medical science. However, blood substitutes are something that we've looked into. A perfluorocarbon blood substitute, for example, carries oxygen approximately 100 times more effectively than our own natural blood, and has been and continues to be used in a medical and surgical practice on a regular basis where a person has lost large volumes of blood and needs the additional blood volume to keep them alive. It is, however, eventually filtered out by the kidneys, so this would have to be maintained going forward. Next, the Spartan's intestinal bacteria is altered to absorb more nutrients. An intestinal bioreactor is implanted and they're given a gut microbiota refresh. An intestinal bioreactor is vague enough in that I can't particularly pass judgment as to whether or not we're capable of doing something like that. I would assume it's something to do with being able to process different types of foodstuffs, but in regards to the intestinal bacteria alterations and the gut microbiota refresh, that kinda is something we can do. It's called a fecal transplant. For somebody who is chronically ill and their gut bacteria has been depleted, or there's only negative, bad bacteria in the gut, a person can receive a transplant of healthy bacteria from the fecal matter of a donor, allowing this new bacteria to take to the gut of the recipient, resetting their gut bacteria and restoring them to health. With some advancement as to what bacterias are good, some more research in regards to superbacterias that may help even further in nutritional uptake, it's entirely possible we could do something similar in the future that would completely refresh our gut bacteria to a point of making us of pristine health. The Spartans also undergo gene therapies, including the lengthening of the telomerase. The telomerase are like the small bits of plastic on the end of shoelaces which stop the shoelace from fraying. The telomerase stops the DNA from corrupting and falling apart each time it divides. Each time the cell does divide, the telomerase is worn down to a point where eventually there is no telomerase left, and this is what's called the Hayflick limit. This is the limit of the number of times a cell can divide before losing the telomerase completely, becoming corrupt, and either being destroyed by the body, the immune system, or self-destructing, or worst case scenario, turning to cancer. Boosting the telomerase defies the Hayflick limit and allows the cells to continue to divide without that corruption. And although it isn't the only mechanism of aging, it's one of the mechanisms of aging. Altering this with the Spartans apparently elongates their lifespan by quite a large margin. In fact, it's said that their fighting days for a Spartan will exceed a century. With a gene editing technique like the CRISPR-Cas9 technique, this is possible, and has already been done experimentally with lab rats, with the result being a massively elongated lifespan for the rats. Now, as with the Spartans being implanted with an array of tiny biomonitoring sensors, we can most definitely do that. Small implanted biomonitoring devices are already relatively commonplace, as well as basic wearable technology that monitors a lot of our biosigns. And finally, the Spartans are given hormone regulation therapies and their bioprofile is archived. Again, this is vague enough that I can't say with any great degree of certainty as to whether or not we could or couldn't do that. I do know we can alter and, in some cases, completely mess around with our hormone levels. Hormone replacement therapy being one that jumps to mind immediately. So while it isn't outside of the boundaries of imagination, I can't see to what means or ends it would be required for a Spartan. And there we have it, that's the last of the Spartan-IV Project Orchid Augmentations. So to summarise, the brain-computer interfaces developed by Neuralink very closely match the profiles of the Torpet data cluster. Muscle engineering can be achieved by injecting follistatin into the muscles. Skeletal engineering can be achieved by lengthening the bones and implanting cross-sectional areas of the bones made of titanium in between, allowing the bone to grow into it. And while reinforcement with a fullerene lattice doesn't immediately make sense, it is at least partially possible. Supermyelination of the myelin sheaths around the nerves, increasing the reaction time of the subject, are completely achievable at the moment with stem cells harvested from bone marrow for treatment for people with multiple sclerosis, and if given to somebody without that condition would result in supermyelination. We are already developing some artificial organ implants in regards to the heart, lungs and pancreas, and others to follow. Increasing the efficiency of the heart can be achieved by implanted bioreactive electroactive polymers, and blood composition alterations can be achieved by using something like a perfluorocarbon blood substitute. Gene therapies for increasing the length of the telomerase can be achieved with the CRISPR-Cas9 gene splicing technique. Biosigns can be tracked by implanted biosign monitors, and with some advancement we could do some hormone regulation therapies, although to what end isn't immediately clear. The takeaway from this being, yes, many of the Spartan-IV augmentations are possible with modern medical sciences and engineering, but the results of these alterations would vary dramatically from what we see in-game. Nevertheless, it would be extraordinarily interesting to see how a human body would respond to such extensive alterations. But, as I discussed in a recent 00 Lounge video linked below, until such time as the bureaucracy, the ethics and the morality are dealt with, and active research actually happens in regards to human augmentation, this is still a good way off. Thanks for watching, commenting, liking and subscribing. I just want to give a quick shout out to my patrons and YouTube members: Spartan-10148, my Metarch, Dylan, Falcon X003, Kenwood, Irrefutable Justice, Leon, Neek and Ramiz, my monitors, Alvin, Andrew, Brand, Brian, Cameron, Chris, Darian, Devon, Flaming Halo, Greenblood, Kyle, Legions Lost, Michael, Prophet Bear, Spartan and Wolf, my sub-monitors, my fleet of Strato Sentinels, my diligent enforcers, and all the other awesome people that have jumped aboard to support the channel over at Patreon. Another shout out to Todd Morrison, my Transcendent YouTube member. And just one quick reminder to support us on all major social media channels, including Discord. Much love from 00. Take it easy everyone, and find peace in the domain.